We've made it to the last big topic in Chapter 7, molecular formulas. These are formulas that are usually used in reference to covalent compounds. Covalent compounds exist as large molecules, and sometimes those large molecules don't have the simplest whole number ratio of atoms. Now, ionics are big crystals that have alternating positive and negative ions throughout the crystal structure. So we report an ionic formula as the simplest repeating ratio of the crystal structure. But covalents really can have large ratios, and that's the true structure of the molecule. So for example, in this first question, we are given an empirical formula for a covalent compound as NO2. Now, number one, it's an empirical formula because it's a simple ratio, 1 to 2. It's a covalent compound because it's two nonmetals, nitrogen and oxygen. If its molecular mass is 92 grams per mole, what is the molecular formula? These two are always related. If I find the empirical formula's mass, let's say take the empirical formula, and I calculate the empirical mass. So I'd be looking at NO2. I plug it in my calculator, and I'd say the empirical mass is approximately 46.01 grams per mole. Here's my empirical mass. Now that's not the true mass of this particular molecule. The molecule that we're looking at has a true molecular mass of 92 grams per mole that will always be given to you. Now all we have to do is figure out how the two compare. How do I get from 46 to 92? Now sometimes it's kind of obvious, or you could take the bigger mass, the 92, and divide by 46, and you should get a whole number 2. If I multiply that 46.01 by 2, I really do get approximately 92, which means that your molecular formula should be double. So here's what I have then. My molecular mass should be double the empirical mass, so I need to double the ratio in the empirical formula. So instead of a ratio of 1 to 2, I'm going to double it and say N2O4. And just for kicks, if I plug that in my calculator, I would be looking at right around 92 grams per mole. So my final answer, what is the molecular formula? N2O4. It should be double the empirical formula. You can always double check and make sure that your molecular formula is correct, because if I add N2O4, I should get the true molecular mass, 92 grams. So these two empirical formulas and molecular formulas, they are related to each other. The molecular formula will just be some larger ratio of the empirical formula. Maybe I double it, maybe I triple it. They will always give you the molecular mass. So let's say we try this one on the bottom. Empirical formula is CH2. So if I just check the empirical mass in my calculator, I'd be looking at about CH2 equaling 14.03 grams. Carbon plus 2 hydrogen. However, the real molecular formula has a mass of 70 grams per mole. Now again, sometimes it's obvious, oh, I double it. Sometimes it's not. So you could always just plug it in your calculator, take the larger mass and divide by the smaller mass. It's approximately 14. And it should give you a whole number, or at least really, really close to a whole number. 70 divided by 14 is about 5. So if I take my empirical formula and multiply by 5, I should get my molecular formula. So if I wanted to double check the molecular mass, that's not molar mass, by the way, that's molecular mass, needed to be 5 times as large. So I'll just multiply my formula, my empirical formula, by 5. So instead of a ratio of 1 to 2, I'm going to make it C5H10. And if I double check in my calculator, 10 carbons, 10 hydrogen, 5 carbon. Yeah, it is right around 70 grams. Give or take a few decimal spots. That is my final answer. C5H10 is a molecular formula. It's a larger ratio of the little empirical formula. Super easy, right? If you have problems like these two, you really don't even need to show work for these. You can do this all in your head, in your calculator. Compare the empirical mass to the molecular mass to find that multiplier. How much bigger is the true molecular mass? Then you'll just multiply your empirical formula by that same little multiplier to get the true larger ratio. Now here's the worst that we could run into. Let's check this next one. Oh, I don't have the empirical formula. Instead, we're given, you got it, percent composition data. We're going to need to calculate the empirical formula. And then we'll be right where we were in the last two. We'll compare the empirical mass to the molecular mass. So I have percent composition data, and I'm going to assume a 100 gram sample so that I have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. I guess it's a good review of empirical formulas. Cancel grams, put it in moles. Carbon's molar mass is about 12.01. And we're going to do this all the way down the line. Cancel grams, we want moles. 1 mole of hydrogen, 1.01 grams. Cancel grams of oxygen, put it into moles. Oxygen's molar mass was 16. So each time we're going to divide, leave a couple sig figs. So maybe 3.33 moles of carbon. How about 6.63 moles of hydrogen? And, ooh, I like this, 3.33 moles of oxygen. These are not whole numbers, and they're not close enough to round to whole numbers either. But, can you see the whole number ratio? Yeah, it's pretty obvious in this one. It's probably a ratio of 1 to 2 to 1, right? Now, if you weren't sure, then you could go through and divide each by the smallest. I'll divide each of these by the 3.33 just to confirm what you're probably already suspecting. I know that's a 1. Divide by 3.33. And that is pretty darn close to a 2. And this should be the 1. So here's my empirical formula. Empirical formula. CH2O. And now we're right where we were on the last couple problems. This is kind of the easy part. The empirical formula is a 1-to-1 ratio. So let's quick calculate the empirical mass. So I got carbon, 2 hydrogen, 1 oxygen, about 30.03 grams. They will always give you the true molecular mass. That has to be given. Its molecular mass, it's 60. So again, And sometimes this isn't so bad. My little empirical mass was 30 grams per mole. The real compound should have a mass of 60. Let's just double it. So to get the molecular formula, we just need to double the empirical formula. So instead of the ratio being 1 to 1, we're going to make it C2H4O2. And if I want to double check, if I add this in my calculator, I would be at like 60.06 grams, which is pretty darn close to 60. So here's my final answer. The molecular formula is C2H4O2. Not bad, right? Should try one more while we're at it? Why not? This one is very similar. While we're looking at carbon, hydrogen, and oxygen, we already know their molar masses. Let's give this one a whirl. Okay, so we have different ratios this time. 64.9 grams of carbon, 13.5 grams of hydrogen, and 21.6 grams of oxygen. It's the same molar masses, so let's plug these in right away. Cancel grams, we want moles. 1 mole of carbon, 12.01 grams. We'll do the same thing all the way down. Do you kind of see how after a while this method starts to become not so bad? You attack every problem the same way. You need grams to put them in moles. Once you have moles, you can get that whole number ratio. Hydrogen, 1.01, and oxygen. 1 mole of oxygen is 16 grams per mole. Alright, so let's see what I got here. I got kind of a funky number. When you get to this point, maybe 04. I'm not going to take off points on your sig figs. When you calculate moles, it's really not your final answer. The final answer is the formula that we calculate. So just leave something that seems reasonable. In the end, we want to get a nice whole number ratio. So if you get too excited and you round them off too quickly, you might not get a beautiful whole number ratio. All right, let's see what we get here. 13.5 divided by 1.01. 13.366 maybe moles of hydrogen, and my oxygen 1.350-ish moles of oxygen. These are not whole numbers and they're not close enough to round, so we're going to go through and divide each by the smallest. Divide them by the smallest, which is this little guy. So I know that's a 1. 1.350. 9.99, which is close enough to a 10. I'm going to say that's a 10. And then we'll do this one, 1.35. Please be a whole number. Yes, it is, 4. So here's my little empirical formula. It's the same elements, but it's a different ratio. It had a different composition. This time we are looking at C4H10O, 1 oxygen. Alright, so we'll calculate the empirical mass. I'll plug this in my calculator. I have 4 carbon, 10 hydrogen, and 1 oxygen for a mass of 74.14 grams. And again, they will always tell you the true molecular mass that has to be given to you. If its molecular mass is 296 grams per mole, what is the empirical formula? So again, like this time, I don't know, I mean the last one was 30 to 60, so I knew that off the top of my head. If you're not so familiar, just divide them. And you can really go like the big mass, 296, divided by your little empirical mass. And you should get a whole number. And I do. 4. So if I were to multiply by 4, I would get the true molecular mass. So that means my molecular formula just needs to be 4 times as large. This one's going to be kind of a big one. My molecular formula. Then would be, C16, good Lord, H40, O4. And if I want to double check and see if that's right, if I plug that into my calculator, 12 times carbon, 40 hydrogen, and 4 oxygen, bingo, it is approximately 296. Perfect. There's my molecular formula. Look at it, it's just a larger ratio of the little empirical formula, usually used with covalent compounds that don't have a simple ratio, because they do exist sometimes as giant molecules.